Continuing our discussion of this antenna problem, in part A we calculated the magnetic flux through each coil. Now in part B, what is the EMF generated in the coil? Well, knowing the magnetic flux in the coil, we can use Faraday's law, and Faraday's law states that the induced EMF epsilon is equal to minus the number of turns times the rate of change of magnetic flux through each coil, d phi b dt. So looking at the magnetic flux here, the time derivative will give us a minus omega sine omega t. So we will obtain minus capital N A E max minus omega divided by omega 2 sine omega t sine Ka over 2. So we can see that the omegas will cancel, the minus signs will cancel, and finally we will obtain the induced EMF epsilon is equal to 2 capital N A E max sine Ka over 2 sine omega t. The term in the parentheses here, the square brackets, will be the amplitude of the oscillating voltage. Moving on to part C, so here we have used Faraday's law. Let's note that. In part C, the electromagnetic wave has frequency f equals 4 MHz and intensity I equals 100 watts per meter square. The coil has capital N equals 50 windings and side length A equals 10 centimeters. It follows that its self-inductance L is 78 microhenries. If the resistance in the circuit is capital R is equal to 100 ohms, what value of the capacitance C results in the resonance frequency of the RLC circuit being equal to the frequency of the wave? So we're looking for the RLC resonance condition. We know that the resonance will occur when the angular frequency is equal to 1 over square root LC, which is 2 pi times the resonance frequency f0. So from this equation we can obtain the capacitance to be 1 over 4 pi square resonance frequency square times the inductance. Now we can plug in the numbers to obtain the capacitance. The capacitance is equal to 1 over 4 pi squared 4 times 10 to 6 hertz, 4 megahertz squared times 78 microhenry, 78 10 to minus 6 henries. This gives us a capacitance value of 20.3 picofarads. Now the last part of this problem asks us what RMS value of the current IRMS flows in that case. Okay, so at resonance we have the inductive reactance equal to capacitive reactance, so that the impedance of the circuit Z is equal to R, which implies that we need to know the maximum voltage and divide it by the resistance R to get the maximum current. Now we have this induced EMF epsilon is equal to 2A capital N E max sine Ka over 2 That's the amplitude. And then we have sine omega t. So we can read from this the maximum voltage, the amplitude of the induced EMF, V max, is equal to 2A capital N, the maximum electric field, sine Ka over 2. All right. So this implies that the maximum current we have in the circuit is V max over the impedance, which is simply the resistance at resonance, R. So this will be equal to 2AN E max divided by R sine Ka over 2. Now we need to calculate E max, and we can calculate the RMS current as I max divided by square root 2. So this will be equal to 2A capital N E max divided by R square root 2 sine Ka over 2. Now for E max, we have to substitute the corresponding value that we will obtain from intensity. But before we do that, this sine Ka over 2 term, we need to know the wavelength. See, the speed of light is equal to lambda times the frequency. So the wavelength is 3 times 10 to 8 meters per second divided by the frequency 4 times 10 to 6 hertz. This gives us 75 meters wavelength, and therefore sine Ka over 2 becomes sine of 2 pi over the wavelength, 2 pi over 75, that's K, and A is 0.1 meters, 10 centimeters, 0.1 over 2. This gives us 0.00419. So we will use this in our calculation. Now, on the other hand, the intensity I, the average intensity, is equal to the magnitude of the pointing vector S average, which is 1 over mu 0 average value of E squared divided by the speed of light. So S average, which gives us the intensity, is E max squared divided by 2 mu 0 C, because time average of E square is E max squared over 2. From this we obtain, which is the intensity here, and from this we obtain the maximum electric field as square root of 2I intensity mu 0 C. So that's what we will use in our calculation. So we will obtain, we also have sine Ka over 2 here. IRMS is going to be 2AN E max over square root 2 gives us square root of I mu 0 C, and then we have divided by R, divided by the resistance R, and sine Ka over 2 So this is our RMS current. Now all we have to do is substitute the numbers here to get the numerical value. The RMS current I RMS is equal to 0.1 meters, 50 windings. The resistance was 100 ohms, so divided by, so let's double check that. The resistance was 100 ohms, yes. So divided by 100. Square root of I mu 0 c, 104 pi 10 to minus 7, 3 times 10 to 8 square root multiplied by 0.00419, and this gives us an RMS current of 813 microamperes. Okay. So in this part of the problem, we calculated the induced EMF using Faraday's law, epsilon equals minus N d phi b dt. So we already know the flux through one coil. We take a derivative with respect to time, and we obtain the amplitude of the induced EMF to NA E max sine Ka over 2. It's oscillating in time with this sine omega t term. The resonance condition is satisfied when the angular frequency is 1 over square root LC, which gives the capacitance value required to obtain the resonance. So we can substitute the numbers to get the resonance. And at resonance, the impedance is equal to R. So I max is V max over R. I RMS is I max over square root 2. So V max over R square root 2. And Vmax is 2AN E max sine Ka over 2. That's the amplitude of the induced EMF here. So sine Ka over 2 can be calculated knowing that C is equal to lambda F. Lambda, the wavelength, is 75 meters, and sine of Ka over 2 then becomes 0.00419. The intensity is, the average intensity is the average value of the Poynting vector magnitude, which is 1 over mu 0 average of E squared over C, which is E max squared over 2 mu 0 C. So this gives us the maximum electric field 2I mu 0 C square root. So we have the maximum voltage 2AN over R multiplied with square root 2I mu 0 C. So this is going to get rid of the 2 here. So we will have 2AN square root I mu 0 C over R. That's the RMS current multiplied by sine Ka over 2. So if we plug in the numbers, we obtain 813 microamps.